Hi students, in this class we are going to discuss about the properties of the DFT, and all you are familiar with this DFT and inverse DFT formula. Now we will go directly to the periodicity property. That is, first, if x of n is the input sequence, its DFT is x of k. If x of n is is having a periodicity with a period n, then x of k will also have a periodicity with a period n. So this is the periodicity property. Next we will see the linearity property. In linearity property, we will consider two input sequence x1 of n and x2 of n. What we need to prove is a1 x1 of n plus a2 x2 of n. DFT is a1 x1 of k plus a2 x2 of k. And you are familiar with all these proofs. Similar to the other we have proved in Fourier transform, Laplace transform, so there is no need to explain it again. Now I will explain this using the problems we have solved it. Now consider this is the linearity property. Now I am going to explain this linearity property with the following example. Consider x1 of n is 1, 2, 3, 4 and x2 of n is 1, 2, 1, 2, and the Fourier transform for this is x1 of k is 10 minus 2 plus 2j minus 2 minus 2 minus 2j, and x2 of k is 6 0 minus 2 0. So these are all we have proved in the tutorial problems. Using the answers I am going to explain it. Okay, now a1 is 2 and a2 is 3. Now perform multiplication with x1 and x2 of n, then you will get this sequence. When you multiply this sequence with 2, you will get 2 4 6 8. When you multiply this sequence with 3, you will get 3 6 3 6. Now I need to add this. I have added this, so I have obtained 5 10 9 14. Now I am going to perform DFT for this sequence. When I perform DFT of this sequence, I will get this sequence 38 minus 4 plus 4j minus 10 minus 4 minus 4j. Now what I need to prove? I need to prove these two sides, right? Now in order to perform this, I am going to check the answers for this. So we know that x1 of k and x2 of k. Now perform a1 multiplication with a1 and multiplication with a2. Now what you will get it? When I multiply with 2, you will get 20 minus 4 plus 4j minus 4 minus 4 minus 4j. When I perform multiplication with 3, what I will get? 18 0 minus 6 and 0. So now I need to add it. So what I will get? I am getting 38 minus 4 plus 4j minus 10 minus 4 minus 4j. Hence it is proved. That is, both are equal. If I add two signals and they perform DFT, or I perform DFT for each sequence and then I add, both the result will same. That is the linearity property. So see here, we are going to perform addition of two signal x1 of 2, x2 of x1 of n, x2 of n here. Before addition, I am going to perform multiplication a1, a2. Then I am performing DFT. The result will be same when we perform x1 of n and its DFT, x2 of n and its DFT, then multiplied by corresponding a1. The result is multiplied by a2. When you add it, both the results of these two blocks will be same. That is the linearity property. Next we will see some of the symmetry properties of DFT. That is, x of n is a combination of real part and that is a complex conjugate, and similarly x of k is a combination of real part and imaginary part. If this combination arrives, what are all the possible output we can obtain? That we are going to discuss in the next topic. Now see, this is the symmetry property of DFT. So if x of n is a combination of real part and imaginary part, similarly x of k is a combination of real part and imaginary part, we need to segregate the real part values of x of k and imaginary part values of x of k. So you know these procedure, right? So if you want to find DFT, we have to use the DFT formula, summation n is equal to 0 to n minus 1. Instead of this x of n, what I have substituted here, xr of n plus j, x of xi of n. Similarly here, cos 2 pi nk by n minus j sin 2 pi k n by n. When you multiply and you split this real part and imaginary part, you will get these answers, right? You can check these answers whether you will get these answers or not. Next we will see the real value sequence. real value sequence. Here the what is the real value sequence is, here if the sequence x of n is real, it follows that is x of n minus k can be obtained from x conjugate of k. So what is the meaning of it is, if one half of the DFT sequence is known, we can obtain the remaining part using this formula. Now I will explain this using some examples, then only you are able to understand. Now see, we have solved this problem, right? 1 2 3 4 4 3 2 1, and its corresponding DFT is 20 minus 5.8 28, like that you will get this answer. You got this answers, right? Now similarly, if I know the first four values, okay, I can obtain the remaining values. How it is? How is it is? Consider this formula. So what I'm going to do is, here n is 8, right? Now I want to obtain x of 5. So we know that n is 8. If I want to obtain 5 here, I have to consider k as 3. So x of 8 minus 3, which is equal to x conjugate of 3. So what is x of 3? Already we know that is nothing but minus 0.172 minus j 0.414. Now when you take complex conjugate, what it will become? It will become minus 0.172 plus j 0.414. So now x of 5 is a complex conjugate of x of 3. So x of 5 is a complex conjugate of x of 3. Similarly, if I want to obtain x of 6, I know n is equal to 8. So if I want to obtain 6, I have to use k as 2. So x conjugate of 2, already here x of 2 is 0, so x of 6 can be obtained by taking complex conjugate of x of 2, so it is 0. Now consider when I need to obtain x of 7, I need to use k equal to 1, so x conjugate of 1. So what is x conjugate of 1? So x of 7 is nothing but x conjugate of 1. So here I have performed this conjugate, so I can easily obtain one half of the sequence. So what is the significance of this is, we can reduce the number of operations involved. Just we can perform complex conjugate so that it is enough to obtain only one half of the sequence. Next we will see some different possible combination. If x of n is real, if it is imaginary, if it is even, if it is odd, what will be the output? We will discuss it now, okay? So consider first one is the real and even sequence. So we know that if x of n is real and even, according to the property, x of k is also real and even. You know real values, right? And also you know what is an even sequence, right? So we have already studied about this even and odd sequence in signals and system, right? So even sequences, that is x of t is equal to x of minus t, that is both are same, both x of t values and x of minus t values are same. Similarly for odd, x of t is equal to minus x of minus t, right? So this is the odd sequence. Now so let us discuss first condition, x of n is real and even, therefore x of k is real and even. So consider this example, x of n is equal to 1 5 1 5 1 5. So this is represent the value at the origin. Now this is an even sequence, right? That is minus 1 and 1 values are same, right? So it is an even sequence and it is also a real sequence. In tutorial class you have find out DFT for this sequence, right? Now what is the answer for this sequence? 0, 3 by 5 and 0. So which is nothing but a real and even sequence. Now consider another combination, that is real and odd sequence. If x of n is real and odd, x of k will be purely imaginary and odd. So in x of n is equal to 2 1 minus 2. So this is the value at the origin. Here it is plus 2, here it is minus 2. So that is odd sequence, okay? So both are that is it satisfying the condition x of n is equal to minus x of minus n, right? So this is an even odd sequence. Now when you obtain DFT for this, what I am getting is I am getting an imaginary sequence. So this is the second combination. Now see the third one. if the input is itself is a purely imaginary sequence, what will be the output? In this case, we have to consider two conditions. One, if the input is purely imaginary and it is an odd sequence. If the input is purely imaginary and it is an even sequence, what is the output we will obtain it? If input is purely imaginary and it is an odd sequence, you will get only a real value sequence. If the input is purely imaginary and it is an even sequence, you will get it, that is the x of k is purely an imaginary sequence. So this is what the different combinations we need to know while performing these DFT operations. Just remember this combination, that is x of n may be a real part and imaginary part. So in real part it may be odd or it may be even, and imaginary part also it may be odd and it may be even. So you have already studied in signals, right? Any signals can be represented by a combination of even and odd, right? Similarly here I have represented in terms of even and odd. So real part is represented in terms of even and odd. So if input is real and even, this will occur. If input is real and odd, you will get this combination. If input is imaginary and odd, you will get this combination. If input is imaginary and even, you will get purely the imaginary combination. So you just remember this so that you are able to check your answers. Next property is the multiplication of 2 DFT and its circular convolution. We have already studied different properties in signals and system. Here the same concept here you are going to do it. That is, here the multiplication of two sequence, that is in frequency domain, which is nothing but the performing circular convolution in time domain. That is, if we perform circular convolution in time domain, which is nothing but the multiplication of the two sequence in frequency domain. Now we will check this, right? X of n is 1, 2, 3, 4 and h of n is this value. So we need to prove this. Okay, now we have to first perform circular convolution, that is x of n circular convolution h of n. So you have done this in tutorial problems and you have got these answer as 7.5, 8.5, 7.5 and 6.5. Now I need to find out x1 and x2, that is here I am going to find out x of k and h of k. So for x of n I have find out x of k, for h of n I have find out h of k. Now I am going to perform multiplication. So what I am getting is I am getting these answers. So this is in frequency domain. So this circular convolution is in time domain. Now I need to check these answers in time domain, right? So I need to perform inverse DFT. So what I am getting is I am getting the same answers. Next one is the time reversal property. If x of n DFT is x of k, x of minus n is x of minus k. So we have proved these properties, right? So now we will see this example. So x of n is 1, 2, 3, 4 and x of k for this sequence is minus 2 plus 2j, 10, minus 2 minus 2j, comma 2. We have done this. We have solved this problem. Now if I perform a reversal, that is here negative sequence will come to the positive sequence and positive sequence will go to the negative sides, right? So this is what x of minus n. So when I perform Fourier transform for this x of minus 1, I will get x of minus k, that is 2 minus 2 minus 2j, 10 minus 2 minus 2j. So what you analyze from this is, if this is x of n, if I perform reversal, the same is applicable in frequency domain also. If it is x of k, then the same thing, the reversal will happen in that is in frequency domain. So you can verify this time reversal property using these example.